Coordinates computer. All right, here's the problem. So example problem, we have I2 gas, iodine gas, plus chlorine gas. That goes to 2ICl gas, iodine chloride. We have our delta G standard of formation of I2 gas is 19.3 kilojoules per mole. Our delta G standard of formation of ICl gas is negative 5.44 kilojoules per mole. And the delta G standard of formation of chlorine gas is 0 kilojoules per mole because it is a pure gas. This is Cl2. Okay, so find the equilibrium constant. Or I guess there's no question mark, period. Find it, find it. Find the equilibrium constant. So I'm gonna let you work this on your own for like 4 minutes. Type in the chat when you get an answer, and then we'll go over it. Sorry, I think one thing I should have told you was that you can assume this is at ambient temperature. So 25 degrees Celsius. That might be the issue. Oh wait, that doesn't make sense. Actually. Okay. Yes. So I'm seeing some people who are getting the right answer. So I'm going to go ahead and go over it. Anybody feel like they need more time? Okay. So for this problem, we're asked to find the equilibrium constant. So we know that the equilibrium constant is represented by this KEQ value. And we have some equations for KEQ. One of them is our concentration of our products raised to their stoichiometric values over the products of our reactants raised to their stoichiometric values, very similar to the reaction quotient. But for this, we don't know concentrations of our product or our reactants, so it doesn't really seem like this is going to be a good option for us. One of the other equations that we have for equilibrium constant is this change in Gibbs free energy of the reaction standard is equal to negative RT ln of K. So here's where our ln of KEQ, a lot of places just write it as ln of K. Here's where our equilibrium constant is hiding. So we do have some information about the Gibbs free energy at standard temperature and pressure. We have our gas constant, which is just always available. It's always the same thing of 8.314 joules per mole Kelvin. And then temperature I provided here. We could assume it's at STP, but STP gets tricky for this because STP for us means 273 Kelvin, but STP in some other situations means at ambient temperature. So I'm just going to start specifying which one I want. So this is, I said STP meaning ambient temperature here. So here's one way that we could isolate for KEQ. but we don't have Gibbs free energy standard of our reaction. We have it for our individual products. So we're going to need to do something to get our Gibbs free energy of the reactants. Okay, so we want to use this equation, Gibbs free energy of the reactants, negative RT ln of KEQ, which if you do log math, this gives you KEQ is equal to E to the negative delta G standard of the reaction over RT. So in order for us to be able to solve this problem, we have temperature, we have the gas constant, we need to figure out this Gibbs free energy of the reaction. So in order for us to figure out the Gibbs free energy of our reaction, this is going to be the summation of the molar values of the Gibbs free energy of formation standard of our products. So the Gibbs free energy of our products minus the summation of the molar concentration of the change in Gibbs free energy of formation of our reactants. So essentially this is similar to enthalpy, you know, products minus reactants, making sure your equation is balanced. For this problem, we have 2 iodine, 2 chlorine. We have 2 iodine, 2 chlorine, so this is balanced. And we have the Gibbs free energy of formation of all of our components. This one we can assume, if we weren't given it, that pure gases have a Gibbs free energy and an enthalpy of 0. Change in enthalpy or change in Gibbs free energy of formation of 0. But it was stated here. So when we plug it into this equation for our products, we have 2 moles of our ICL gas, which is negative 5.44 joules per mole. That's our only product. Minus our reactants, which is 1 mole of I2, 19.3 kilojoules per mole. And then plus our 1 mole of 0, so plus 0. And this is for our reactants. So our products minus reactants gives us a delta G standard of our reaction to be negative 30.18 joules Ooh, golly, I need to. Sorry, everybody. This is kilojoules, right? So this was kilojoules, this is kilojoules. In order to add these, this needs to be kilojoules. So this is kilojoules. In my note, it said kilojoules, but I've been in meetings all morning and I haven't even had time to eat. That's why I'm like eating here. So I think my brain is at the end of its life already and it's noon. All right, so negative 30.8 kilojoules per mole. On an exam, I would typically give these to you in some sort of table format. I wouldn't just write them for you. Okay. All right, so now we know our change in Gibbs free energy of our reaction, and we have everything that we need to solve our KEQ. So if we put our Gibbs free energy change of our reactant to be negative 30.18 kilojoules per mole, then get rid of these. So now we have KEQ is equal to E to the negative delta G of our reaction standard over RT. We have E to the negative 30.18 kilojoules per mole divided by our gas constant of 8.314 joules per mole Kelvin times our temperature, which is 273 Kelvin plus 25 degrees Celsius to convert to Kelvin. But here I have a mismatch between kilojoules and joules. So I'm going to convert this from 1 kilojoule into 1,000 joules. So now my units will be joules per mole divided by joules per mole Kelvin times Kelvin. So my units will all cancel out. If I work this, this gives me E to the positive 30,180 divided by, I think this is, when I did this, 2,477. I think that's what it worked out to be. But then this math gives you E to the positive 12.18. When you type this into your calculator, you don't get an overflow this time. You get about 1.95 times 10 to the 5 as your KEQ. Oh, I see what you're saying. Okay, so yeah, it could be. I get really sloppy with this delta G, like kilojoules per mole or just kilojoules. But for this reaction, I have like 1 mole of my like desired reactant being reacted. So this is actually like kilojoules per mole of 1 mole of I2. So on the exam, this was similar, like for benzene, it was your reaction was kilojoules per mole for every 1 mole of benzene being reacted in this problem. So yeah, this is essentially saying that for this reaction, for every 1 mole of like I2 gas that I'm reacting, I have this. So kilojoules per 1 mole of iodine is like actually what this is saying. So you could also write this as negative like kilojoules per mole, or I'm sorry, just kilojoules. For enthalpy and delta G, I should be like more consistent about which way I'm writing these, but as long as you have like 1 molar unit here, then it doesn't really matter because you're saying like per every 1 mole of this reaction, this is my delta G that's being produced. You run into issue when you have something like 2 molar here, because now this is your value, but it's not per every 1 mole that's being reacted. So this is actually twice as high as it needs to be. So yeah, that you can write this either way. I wouldn't have taken off points for either way that you write it. Kilojoules would have worked fine here too.
So Dr. Redfern, if that's the case, we'll have a problem canceling out the R if the top is kilojoule and down there we have kilojoule per mole.
Right, which is why I wrote it here to make sure my units cancel, but it's the same reason that I would like that it works either way up here, because my mole is hidden in my reaction. So in the reaction of 1 mole of my iodine gas, I'm producing negative 380 kilojoules. So I'm saying the same thing, like essentially either way. But in order to make sure that your units are like canceling here, you need to recognize that this is per every 1 mole of, like you could write it like this. Right, because this is saying the same thing. So for this reaction, I have negative 30.18 kilojoules, but this reaction is 1 mole. So you can either write it as kilojoules per mole or saying that this 1 molar reaction is producing this amount. It's the same exact thing. Yeah, as long as this has 1 mole of your like the reactant of interest. your gas constant is also applying like per 1 mole that you're reacting. So that's why it's important to make sure it's like per mole. All right, so is this KEQ going to be product favored, reaction favored, or a little bit of both? Yeah, so this is going to be highly product favored. Remember, if it was like greater than 1,000, KEQ was greater than 1,000, it was pretty much all products. So this reaction is going to be very product favored. It's going to really like to proceed forward. So yeah, that's what we know. If I gave you a Q of let's see, 1.95 times 10 to the 4, which way would the reaction proceed? So my reaction would proceed forward because my Q is less than my KEQ, right? So my KEQ is 10 to the 5, my Q is 10 to the 4. So it's a magnitude a magnitude of difference. So my reaction, if my Q was given as a 10 to the 4, my reaction will continue to proceed forward. Does that make sense to everyone? No, I have water, thank you. All right. So I have another problem. Okay, a reaction has a change in enthalpy, of negative 28 kilojoules, and a change in entropy as negative 60 kilojoule or 60. Let me check what this is supposed to be. Oh, yeah, okay. And a change in entropy of negative 60 joules per Kelvin. So these are actually supposed to be joules and kilojoules this time. At what temperature will it change from spontaneous to non-spontaneous? At what temperature will it change from spontaneous to non-spontaneous? Please type in the chat once you have a value. Okay, so I've gotten a few correct answers. Does anybody need more time working? Okay, so this equation is pretty obvious which one you're going to use. You're going to use our change in Gibbs free energy is equal to our change in enthalpy minus our temperature times our change in entropy. It is important to note, and I said this in presenting this equation, your temperature is always Kelvin. Always. It has to be a positive number. So it's always going to be something that's greater than 0. We can't physically reach 0 Kelvin. We haven't accomplished it. So it has to be something greater than 0. So we also know that spontaneous is a delta G that's negative, and non-spontaneous is a delta G that's positive. So we're going to have this equation turn from spontaneous, so a negative value, to non-spontaneous. So this is going to have to be a value that is greater than 0 for G. And then we're given our change in enthalpy and our change in entropy. So we just have negative 28 kilojoules here, minus our temperature times our negative 60 joules per Kelvin. But we have this mismatch in units here. So I'm going to convert one of them. I converted this 60 over here, where I have 1 kilojoule is 1,000 joules. So I have 0 is equal to negative 28 kilojoules minus a temperature term times a 0.06 kilojoules per Kelvin. If you move the 28 to the other side, and then you divide both sides by 0.06, this is kilojoules, this is kilojoules per Kelvin, which leaves out the units of Kelvin. This is going to be equal to your negative temperature. So, nope, it's not, because this, I'm sorry, I left this negative here. So this is, the negatives canceled. Okay, so this was negative 60. So that's why this should actually turn to positive. So this is your positive temperature. I was wondering where that went. So when you do this math, your temperature is equal to 466.6 degrees Kelvin as our temperature, where we switch from spontaneous to non-spontaneous, a delta G that's negative to a delta G that's greater than 0 or positive. So that's pretty hot that we turn from spontaneous to non-spontaneous. And it's interesting that at really hot temperatures, we would turn to something that's considered to be non-spontaneous, because a lot of times it's the hotter you are, the more spontaneous. So just interesting. Any questions about this? Okay. Here's another example. Fill in the blank, use the chat. A system with blank and blank will never be spontaneous. A system with blank and blank will never be spontaneous. So think about on your homework and in class, we have that, like the 4 quadrants. Yeah. Great. So we have this equation again, the one we just worked. And in order for us to have spontaneity, we have to have this value be less than 0, so a negative value. And in order for us to get a negative value, we either have to have a condition where this is negative and entropy is positive, or where the magnitude of this negative enthalpy is larger than the magnitude of this positive entropy times temperature, or the magnitude of this positive entropy times temperature, I'm sorry, positive entropy has to be greater than the magnitude of this positive enthalpy. So remembering that quadrant that you had to make for the homework, like when are you never going to be spontaneous? This is when you have a positive change in enthalpy and a negative change in entropy. Because then you're going to have a positive here, you're going to have minus a negative, which will give you a positive. So you will never be able to reach a negative delta G if you have a positive enthalpy and a negative entropy. Oh, golly, too much nomenclature. Okay, great. So okay, example here. Would you expect products or reactants to dominate at equilibrium? Would you expect products or reactants to dominate at equilibrium when our delta G standard is A, 1.4 kilojoules per mole? So would you expect products or reactants to dominate at equilibrium when your delta G is 1.4, positive 1.4 kilojoules per mole? So for this problem, I would probably say both, right? You're going to have kind of a mixture of both products and reactants. That's a very close to 0 delta G. And so it's kind of going to be like a little bit of reactants or a little bit of products. So I would say, what about for 105 kilojoules per mole? Are you expecting more products or more reactants? Wait, it seems like there's kind of a good amount of confusion about this. So for this, we would expect reactants to dominate because this is a delta G that is 105 kilojoules per mole. So whatever equation that we have here, our delta G is going to be 105 kilojoules per mole. And this is going to be non-spontaneous. It's a pretty large positive number. It's not going to want to proceed this way. It's not naturally going to proceed spontaneity towards this direction. So we're going to assume that there's more reactants than there's products because this is not proceeding forward. This is not spontaneously creating products. So what about negative 34 kilojoules per mole? Yes, because it's positive and because it's not super close to 0. 0 is going to be like kind of mostly it's going to be kind of floating back and forth, right? Like probably a little more reactants would be favored, but 1 is such a low delta G, you know. So what about negative 34 kilojoules per mole? Yeah, exactly, Emma. So this time we're going to have some spontaneous movement towards our products. So if our delta G is at negative 34 kilojoules per mole, we're going to say it's going to be favoring the products. It's spontaneously going forward. We are going to see some spontaneous reaction between our products to produce our reactants. We don't know anything about rate, but we're going to say that this is producing products, but this is a relatively small value. We just saw, we've seen delta G's that are in the thousands. And so this is pretty small. I would say it's probably going to still be a mixture of reactants and products, but mostly still favoring products. All right. Any questions about this? Okay. All right. So here's another question. Normally I do these as like kind of Jeopardy style questions where you're like on a team on a whiteboard and there's like a competition. So it's normally like more fun, but oh well. All right. The enthalpy, the change in enthalpy and change in entropy of a reaction are both negative. Is the reaction spontaneous? Any other people want to chime in? Is this reaction spontaneous?
Temperatures.
Yep. Yeah, so we aren't told anything about the magnitude of these. We're just told that it's negative. So this could be like negative 0.001, and this could be negative, 4,000 joules per Kelvin. So we're not really told anything about magnitude. So along the lines of it's temperature dependent would make sense. So if you put on, like, this would be an example of a conceptual question on an exam. If you put at low temperatures or temperature dependent, I would accept that. But another even more correct way would be to say if the magnitude of H is bigger than the magnitude of T times delta S, right? So essentially, if this is more negative than this unit, since this is a negative value, this will become a positive. So you have these like fighting forces, right? Some negative heat being released, it's exothermic, but it's also, this is going to turn into a positive unit. So if this is more negative than this becomes positive, you'll still be spontaneous. A lot of times that means if the temperature is low, because the lower this temperature, the lower this magnitude is. So you're kind of saying the same thing, but to be absolutely correct, you would need to say like if the magnitude of the enthalpy is bigger. Any questions about that? I mean, this whole equation is temperature dependent, but yeah, it would be temperature dependent. Yeah. I mean, if these were both like, if this was a negative 1000 joules and this was negative 1000 joules per Kelvin, it would you would have to have like your temperature be really low or higher in order to flip it one or the other. So in general, yes, that would be a temperature dependent case. Yeah. Okay. All right. Here's an example. I pulled this from an MCAT test booklet. If the reaction quotient is greater than the equilibrium quotient, the reaction quotient is greater than the equilibrium quotient, what is true about Gibbs free energy? So use the chat. What's true about Gibbs free energy if the reaction quotient is bigger than the equilibrium quotient? Yeah. So Noah and Dan have said the same thing, and it's pretty much the answer. But what the way I phrase it was, it is greater than 0. It is greater than 0. You could also say it's non-spontaneous, or you could say it's positive. These are all three saying the exact same thing, right? Delta G is going to be greater than 0, it's going to be positive, or it's going to be endogonic. And this is because we have our Q line, right, where we go from 0 to infinity. We have some KEQ that we put here, and our reaction quotient Q is greater than our equilibrium quotient KEQ. We don't know how much greater, we just know it's greater. So we know that our reaction is going to be proceeding in the reverse. So we have some sort of reaction that's happening. And we know that we are not going to be going towards generating products as we try to reach equilibrium. We're going to be generating reactants, which means we are no longer spontaneously moving forward. We are not trying to go to produce more reactants. We are trying to go the other way, which means our delta G would be positive. It would be non-spontaneous. It would be endogonic. Any questions about that? Okay. So I have this problem here. I have N2O gas. I forget which one this is. Nitrous oxide, one of those. Plus 3O2 gas will react to create 2 in, oops, I don't want to balance it for you. Got carried away. Okay, O2 gas. Well, now you know it's not balanced. Plus N2O4 gas. Find KEQ. given 2 N2 gas plus oxygen gas goes to 2N2O gas. KEQ of this first reaction is 1.2 times 10 to the negative 35. 2N2O4 gas goes to 10NO2 gas. KEQ2 is equal to 4.6 times 10 to the negative 3. And 3, 1/2 N2 gas plus oxygen gas goes to NO2 gas. KEQ of 3 is 4.1 times 10 to the minus 9. So find KEQ of this overall equation. Okay.
So I think this question's pretty tricky. I'm probably going to start going over it. Anybody would like more time to work on it yourself? Let me know in the chat. Does anybody want a little more time to try to get through it yourself? Okay. How about I give another like 4 minutes? So at 12:34, I'll go over it.
All right, I'm gonna go over it unless anybody would like some additional time. Okay, so the way that we work this problem is similar to the problem that we worked on the last exam. Um, and we worked in several examples where you have to do some sort of like rearrangement, manipulation of your given equations here, to make it work. Sorry, there's a bird in our yard and Beefy is like so interested. It's cracking me up. He hasn't moved. He's like so straight, really intense. He's so still. It's so funny. He hasn't moved for like a solid 5 minutes. It's a bird. It's like a heron that's standing like right outside. Yeah, he's really invested for some reason. All right, so we know that we need to first check that this equation is balanced. These all come balanced because they have KEQs associated with the given balanced equations, but we need to check that this is balanced and it is not. So we need a 2 here, a 3 here, and a 2 here. So now we have 4 nitrogen, we have 6, 8 oxygen, we're balanced. So now we're looking for this, how to make this overall equation to wait, is that right? Yeah, 2 into O. I have that written wrong in my notes. Plus 3 into O gas plus 3 O2 gas goes to make 2 into O4 gas. And in order for us to be able to make this, we're going to need to do some manipulation of these. So everybody starts a different way. I like to start like one at a time. So I am going to pick like this first chemical here, which I find in my first equation here. But I can see that it's on the wrong side. So I'm going to need to reverse this equation. And I need to reverse. And in order to reverse my KEQ, this becomes 1 over KEQ. When you reverse, this becomes the inverse. So if I do 1 over 1.2 times 10 to the minus 5, this is going to be a huge number because this number is tiny. So the way my reaction is currently set up is this says that I'm going to be so unbelievably favoring the reactants that it's almost not going to have anything happen ever, right? Like I am so far negative that I am all reactants, right? Remember KEQ is your products to their powers over your reactants. So if you have a really, really small number, that means that these reactants are so big, or your products are really, really small, either way. But if you invert it, then you're directly inverting that and you're becoming product favored. So that's why you have to do the inverse of this. So if you invert this, you get 8.3 times 10 to the positive 34 as your KEQ. I have 2 moles of this that I'm desiring here. I have 2 moles of this that I'm getting here. So if I reverse it, I don't need to do any other additional multiplication for that. I'm going to get my 2 into O. Then for my next chemical, I'm going to look at oxygen, but I see that I have oxygen in both this equation and this equation, which means it's going to be a little more complicated. So I'm going to skip it and come to this one because this one only appears in one equation here. So I can tackle that one without having to manipulate and make sure 2 equations work out. So here I want 2 moles of N2O4 and I want them on the right-hand side. So I'm going to need to multiply by 2 and reverse. So I'm going to reverse this and multiply it by 2 to get 2 N2O4 on the right-hand side. So in order to do this, I'm going to need to first raise this to the second power and then invert it. So this is like 1 over KEQ squared. Because if you remember KEQ math, if you multiply by 2, you have to raise it to the power of 2. If you reverse it, you have to invert it. So when I do 4.6 times 10 to the negative 3 squared, this gives me 2.1 times 10 to the negative 1, 2, 3, 4, 5. And then I do the inverse of that in my calculator. This gives me about 4.73 times 10 to the positive 4. All right, so now I have this one taken care of. Now I need to see how I can get my 3 oxygen to cancel. So based on the equation I currently have, I have 1 oxygen on the right-hand side and I have 1 oxygen on the left-hand side. But I want to have 3 oxygen total. So I'm going to need to have 4 oxygen on the left-hand side and 1 oxygen on the right-hand side. So if I'm going to check to see if that would work. If I put a 4 in front of all of these, would that make sense? So I would have 4 N2, which would cancel. I'm sorry, I'd have 2 N2, which would cancel with my 2 N2. I would have 4 NO2, nitrogen dioxide, and I would have 4 on the left-hand side, so these would cancel. So that it looks like when I multiply everything by 4, I would get my 3 oxygen and I would have my NO2 and my N2 cancel, which is good because they're not in my final equation. So that works. We need to multiply everything by 4, but we don't need to reverse anything. So the only thing we need to do here is raise this to the power of 4, which gives me my KEQ for this one as 2.8 times 10 to the negative 34. All right. And then what I can do for my overall reaction is I can just add these all together, right? Wrong. You don't add, you have to multiply for KEQ. So there's a lot of similarities between enthalpy and Gibbs free energy and how we work these, but for KEQ, everything is more complicated. So KEQ, we have to multiply them. 8.3 times 10 to the 34. Yeah, that's a common mistake. 4.7 times 10 to the 4. 2.8 times 10 to the negative 4. And so this gives you overall about 1.1 times 10 to the 6 as our KEQ. So is this reaction product favored or reactant favored or a little bit of both?
Product.
Yes. So this is product favored, highly product favored. We're pretty much only going to be product. Are there any questions about this? How to do this? All right, well, it is 12:47. So I think we're done for the day. Wednesday will be a review of the exam. So I'll be going over chapters 4, chapter 5, Gibbs free energy. And then Friday is the optional in-person exam final or exam 4. If you want to take it on Friday, please show up at 11:30 in the classroom. If you don't want to take it on Friday, please use that time to study or work on your other exams. There's no class on Monday the 26th. So if you take the exam on Friday, you are then done with thermo. If you don't take it on Friday, you need to show up on Saturday, May 1st. In this class, I don't drop an exam. It's not optional, unlike in fundies. So, make sure, I have graded all of exam 3, but I had 2 people who needed to make a makeup. So I don't want to post the exams until I have everybody or post the grades and talk about anything until I have everybody who have taken the makeup exams. I think my average was much higher for this exam than last time. Currently, right now, it's sitting at like 80, I think. It's not bad. Yeah, this Friday, the 23rd, is your first optional final day. Yeah, sure, let's see some chickens. Oh, I can hear them. Oh, wow. Do they make eggs?
Yeah, they do.
Oh, I love it. I need to get some chickens, but Beefy would probably kill them. Wow, they're so cute. I love them.
Yeah, they lay like 7 eggs a day.
That's
We
my
have some-
dream. Wow, that's great. Yeah, everybody bring your animals to class. I really enjoy it. Thanks, Emma. Okay, so any questions before we conclude for the day?